So let's talk about heats of reaction. And when we're talking about the heats of reaction, we're talking about the amount of heat that is exchanged between the system and surroundings while a chemical reaction is taking place. All right? And what you'll find is that nearly all chemical reactions involve some heat exchange between the system and surroundings. And that will be the focus of our discussion for this and for this section and other sections we'll be meeting later on. So at this juncture, we need to introduce some other terms here. You may have met these terms before in your introductory or high school chemistry courses. Exothermic and endothermic reactions. So let's talk about exothermic reactions. An exothermic reaction is one that produces heat, all right? Now, if this reaction is taking place in an isolated system, the temperature will rise as a result, all right? Because heat is produced. And the result also is that the system will go from a higher energy state to a lower energy state. And therefore, the heat of the reaction represented by Q reaction here will be negative. So that's basically what happens in the case of an exothermic reaction. The endothermic reaction is opposite to what we just discussed. It's a reaction that will absorb heat, and in an isolated system, the result of that would be that the temperature will decrease. And a system, or the system in this particular case, will go from a lower to a higher energy state, which means that Q reaction will be positive, all right? So that's the difference between an exothermic and an endothermic reaction. And just to give you some examples of processes that are exothermic and endothermic, I'm just going to talk about it here. If you take a test tube with water and you add a few pellets of sodium hydroxide to it, and you stir it to make sure it dissolves, and if you were to feel the outside of that test tube, it's going to feel warm or even hot, depending on how much of the sodium hydroxide you add to it. So what that indicates is that the process of dissolution of the sodium hydroxide in water is an exothermic process, because basically it produces heat, which of course is transferred to the surroundings. So when you feel the test tube, it's going to feel hot. On the other hand, if you were to take a test tube of water and add to it some potassium nitrate and you feel the outside of it, what you're going to notice is that it's going to feel cold. And that's because the process of dissolving potassium nitrate is an endothermic process. It absorbs heat from the surroundings, and therefore that's why it feels cold to the touch when you're dissolving sodium nitrate or potassium nitrate, for that matter, in water. So those are just two examples of, well, in one case, an exothermic process, and the other one, an endothermic process. Okay, so what we're looking at here is some hypothetical examples of what happens in different systems for an exothermic reaction. And if you understand this, then you should be able to predict what will happen in the case of an endothermic reaction. All right, so here we have a purely hypothetical situation where all the heat that is generated in an exothermic reaction in this vessel escapes into the atmosphere or into the surroundings, right? So basically, what will happen is that the temperature will not change for that system, all right? Basically, the system temperature will remain at 25 degrees in this particular case, where the temperature of the surroundings will be 25 degrees, and that's because all the heat that is generated basically goes into the surroundings, all right? That is purely hypothetical. Very unlikely to happen, because most often than not, in real life, what will happen is described in the second case right here. So in the second case, what happens is that not all the heat will be released to the surroundings. Some of it will be absorbed by what is remaining in the vessel, right? So in this case here, that amount of heat that is absorbed by what is remaining here will result in an increase in temperature from 25 degrees Celsius to about 32.2 degrees Celsius in this particular case, all right? That is what you'll most commonly observe in real life. If you have a reaction in a beaker and it's exothermic, this is more accurate in terms of describing what happens compared to the previous example that I showed you before. Now, in this case, the third case, what we have here is an isolated system. If you remember, an isolated system does not allow for heat or matter to exchange between itself and the surroundings, all right? So in this particular case, there's no heat exchange between the system and surrounding, and therefore all the heat that is generated in this exothermic reaction will be absorbed by whatever remains in this system. So basically, the temperature increase will be higher. As you can see here, it's 35.4 degrees Celsius compared to the 32.2 degrees Celsius, all right? And this is a system that we use very often in order to accurately measure the amount of heat change that takes place in a reaction, because in the isolated system, we can basically not allow for heat to escape into the surroundings, and therefore we can measure the amount of heat change that is taking place, and therefore we can do some calculations to find some other things. Okay, including the heat of the reaction. All right, so that's basically what happens in the case of an exothermic reaction. And as I said before, if you understand this, then you should be able to predict what would happen in the case of an endothermic reaction in each of these cases. All right, I won't go into that, but I leave you to think about that and figure that out on your own. Of course, if you have any questions, feel free to contact me and I'll help you to understand what will happen in the case of an endothermic reaction in each of these cases. Okay, so let's move on now to talking about the internal energy change that takes place in a process where the volume is kept constant, right? So what we're talking about here is that the change in volume is equal to 0. Now, if you remember, we said, and let me write this here, that the work done on the system, W, is equal to minus P delta V, all right? So if delta V is equal to 0, that means that work is also equal to 0, which is what is stated here. And since delta U, the change in internal energy, is equal to Q plus W, as according to the first law of thermodynamics, if W is equal to 0, then that means that delta U is equal to Q, all right? So therefore, what that means is that the change in internal energy will only be due to the heat change that is taking place in the system at a constant volume, and we can represent that Q by Q sub V, where V represents the fact that the volume is constant, all right? So that's what happens in systems where you have a process taking place, but the volume does not change. There's no expansion, there's no compression. The volume does not change, which means that all the internal energy change in that system will be due to the heat change that is taking place in the system, all right? So that's basically what this is saying here. All the thermal energy produced by conversion from chemical energy is released as heat. And this is obviously talking about an exothermic process. There's no pressure volume work being done because there's no change in the volume. If there's no change in the volume, that means that there's no work done by or on the system, all right? Now, again, in real life, this is very unlikely to occur. What is more likely to occur is where the internal energy change will occur when there is constant pressure, not constant volume, but constant pressure, all right? So let's look at what happens in that case. So we're going back to the same equation here, where delta U, let me rewrite this up here. Delta U is equal to Q plus W. Okay, so in this case here, we're talking about constant pressure. So therefore, we can put a P here, which is what we have here. And W would be equal to minus P times delta V. And we can rearrange this to get an expression for the heat change at constant pressure. And that would be equal to delta U plus P times delta V. So what this tells you is that most of the thermal energy is released as heat, but there'll be some work that is done to expand the system against the surroundings. And again, we're assuming we're talking about an exothermic process, right? So basically, that is the result of the internal energy change at a constant pressure. Basically, what it comes down to is this equation. QP is equal to the change in internal energy plus the pressure volume work that is done on the system, all right? So that is basically what happens under constant pressure, which is what happens in the vast majority of cases when you consider chemical reactions, because the pressure that is normally exerted on a system is atmospheric pressure. even though you can actually alter that, you can create conditions where the pressure is changed, but the point of the matter is that it is constant, and therefore this is the relationship between the heat change under constant pressure, the change in internal energy, and the pressure times the change in volume. All right? Now, based on this here, we can define what is known as the enthalpy, right? The enthalpy is the sum of the internal energy change and the pressure volume product of the system. So this is basically what enthalpy is. H is the symbol that is universally used for enthalpy, and that is equal to U, which is internal energy, plus P times V, the pressure times the volume. So, as we said before, we were talking about the fact that under constant pressure conditions, QP, right, based on this equation, would be equal to delta U plus P times delta V. In other words, QP would be the same thing as the change in enthalpy. So basically, the heat change under constant pressure conditions is basically the same thing as a change in enthalpy. And over here, you see a diagram showing you what happens when magnesium is added to a solution of hydrochloric acid. It's a reaction that produces hydrogen gas. That gas expands against the universe or the surroundings, and as a result, exerts pressure, right? And therefore, the relationship between the heat change under constant pressure, which is enthalpy, would be equal to the change in internal energy of all the materials inside here, plus the pressure times the change in volume as it relates to the gas that is produced, all right? So enthalpy is basically a very important measurement that we use in order to express the change in internal, change in energy, heat change of a system as a reaction is taking place. Okay, we're going to stop here, and then the next topic we're going to discuss is the different properties of enthalpy, and we're going to do some calculations involving enthalpy as well. Okay, until next time.